Cool. So today we are going to continue our lecture on the quantum machine learning, and this is the part 2. And in the part 1, we actually introduced some basics of the quantum computing, how the qubits works, how we can implement different kinds of the qubits, and also what are the basic gates, and how to implement a very basic quantum classifier. And also what is the status of the current quantum computing, for example, the noisy intermediate scale, the NISQ era, and also how to perform some of the compilation on those NISQ devices. And today we're going to further to introduce more details of the quantum machine learning. Specifically, we're going to introduce parameterized quantum circuit, or called PQC, and also how to train those PQCs to finish some of the specific tasks like the quantum classification, and also how to perform noise-aware on-chip training to improve the robustness and also reliability of the quantum parameterized quantum circuit. And also, we are going to introduce a library, which is a TorchQuantum Library developed here at MIT to perform those quantum machine learning tasks. And finally, we're going to introduce for different kinds of the architecture we can use, how can we choose the one with the highest reliability to do those quantum machine learning tasks. Okay, so for the first section, we are going to introduce some of the basic taxonomy of the QML approaches. So basically, we can have two dimensions. One is the types of algorithm, right? So we can have a quantum algorithm or a classical algorithm. And also we have type of data, classical data or quantum data. So in that case, we can separate this whole landscape into 4 regions. And on the top left corner, that is the classical data, classical algorithm. And we already learned a lot of those different types of the classical efficient algorithms for classical deep learning in the previous lectures. And also we have those classical data quantum algorithm. So that's how we can use the power of quantum computing to process the classical inputs such as the images. And that's what we are going to introduce in this lecture. And also for others, those quantum data classical algorithm, those are typically referring to how to perform the control of the quantum devices, like how to send different control signals to the qubits, how to do the calibration, and also how to read out. And finally, we also have this quantum data, quantum algorithm. That means you can also process some of the quantum information. For example, you can use the qubits as a sensor, right, to sense some of the environment. And then you want to decode what is the information we can get from the quantum qubits sensing. And then in that case, we can use also quantum algorithm to process the quantum information. But in this lecture, we are mainly focusing on how to process the classical information, classical data with the quantum algorithms, which is the second line of the taxonomy. All right. So first of all, we want to understand the concept of the parameterized quantum circuit. So in the last lecture, we introduced in the quantum circuit, basically, we have multiple stages. We want to initialize the qubits and also then apply in different gates. And finally, we can do the measurement to obtain this classical outcome from the quantum information qubits. So here is an example for the quantum circuit, parameterized quantum circuit. We can see some of them has this yellow color, which contains those parameters or tunable values. So that means, for example, this Rx theta gates, you actually can configure the rotation angle of this gate. And for different rotation angles, the actual effect of the gates will be also different. And for other ones in the gray color, such as the C0 gate or the X gate or the H gate here, so those are the fixed gate. So that means those are basically the ones that is performing the fixed operation. So just like in the classical deep learning, we have multiple layers, right? Some of the layers, such as the convolution or the multi-layer perceptron layers, they have the ways to tune. However, there are also some downsampling layer, right? Like the max pooling or some other flattened layers, though they don't have any of the parameters to tune. So one thing that we are caring about this the property of the quantum circuit is the expressiveness or the expressivity. So we want to understand how expressive is the quantum circuit to represent arbitrary states, how the circuit can cover the Hilbert space, right? So here actually the extent to which the states can generate from the circuit deviate from the uniform distribution can be characterized as the expressivity of the quantum circuit. So here we can see 2 examples. One is on the left. the quantum circuit A, which has firstly a Hadamard gate and also the rotation Z gate. And on the right-hand side, we have another circuit which have one more operation or one more parameter. So we can firstly rotate on the Z basis with this RZ gate. And then after that, we also apply a RX gate with the phi parameter here. So it is very intuitive that if we have more parameters, right? For example, on the right-hand side, we have a larger expressivity, which means we can represent more state in the whole Hilbert space. So how exactly can we visualize this, right? So here on the top side, we can see the circuit A. When we actually changing the theta values here, we can see the coverage of the block sphere on the top right corner here is actually a ring on the tropical here. And then for the circuit B here, we actually can have a more larger coverage of the whole space, because after we have a different combination, different random assignment of those theta and phi values, we can have a coverage of the overall space. So it's not just limited to a ring of this block sphere. So in that case, we can understand actually visually or intuitively, the circuit B here has a better representation power compared to the circuit A. So in other words, actually we can have a more rigorous definition of this expressivity. So here we have more examples. The first one, we have the idle circuit, which does nothing. And also we have circuit A, B to the arbitrary unitary rotation. So if here we want to compare, we want to understand what is the coverage of this whole space with this given quantum circuit. So here we are actually comparing the circuit to some of the arbitrary state, which is called hard measure. So here on the bottom side, the hard measure is actually measuring that it's a uniform distribution. So that means for two arbitrary states in the Hilbert space, what will be the difference between those two states, right? So for example, we can do a sampling, and then we can sample many different pairs in the whole space. And then we compute what is the difference between those two. It can be computed as the infidelity between the two states, right? In that case, we can imagine for a single qubit that's actually uniform, right? So because we can sample two states which are very close to each other, we can also sample two states are very far from each other. So the distribution of that is actually arbitrary. And also, if we want to evaluate the expressivity of a given circuit, and then the way we do that is that we can randomly sample many different pairs that can be represented by the circuit. So specifically, in order to do that, we can sample two different values of the RZ gate and then compute the fidelity of that. So in that case, we can also have another distribution shown in the yellow distribution here. So in that case, we want to compare what is the KL divergence between this yellow distribution to the uniform distribution. You can imagine that if we have just an idle circuit, and then no matter what we sample, we always get the same state. And then the fidelity of that will be always 1. So in that case, there is a very large value or large probability in the first figure here that we have a 100% of 1 fidelity here. And then in that case, if we compute the KL divergence of this distribution to the hard measure, and then the value will be extremely large. And then if we have the arbitrary unitary here, and then if we just compute the distribution of this uniformly sampled two states, and then we can know the fidelity of that can be very close to the uniform distribution. And then the KL divergence of this distribution to the uniform distribution, the hard measure, will be very low. So in that case, you can imagine the lower the KL divergence here, that means the higher the expressivity of the quantum circuit. So besides this expressivity, we also want to understand what is the entangling capacity of the circuit. So we want to know, like say, given this circuit, whether we can entangle the states of two qubits. So here we can use a Mayer-Wheelock performance measure to tell us, or called the MW measure. So for the MW measure actually have a range of 0 to 1. And if for an unentangled state, and then we can compute the MW measure at 0. And for four entangled state of two qubits, and then the MW measure will be 1. So in that case, we can actually use an averaged MW measure to measure this entangling capability of the quantum circuit. So here we can firstly have a look at the many different kinds of the quantum circuit structure. So for example, the circuit 1 here, we only have those gates on the each of the individual qubits, right? So there's no quantum gates between the two qubits at all. So in that case, there is no entangling between any of the qubits, because if you don't do any gates between the qubits, how you can entangle those two, right? So we can also see the qubits circuit 2 here. We have many of the CNOT gates between the qubit 4 to third, qubit 3, and qubit 3 to qubit 4, qubit 2, and also qubit 2 to qubit 1. Right, and also we also have other circuit with different structures. So for other circuit, we can always see that there are some entangling power between the qubits, which means you can do the this entangled state preparation using this quantum circuit. So there are more circuits that can be constructed with different structures here. So here we can actually leverage this MW measure to have a visualized plot of this entangling capacity of all the quantum circuit. So here we have different colors first. So different colors means that how many layers you can apply this block. For example, you can just apply a single block here, or you can apply multiple copies of the block to prepare those entangled states, right? So first of all, we can see that for the circuit ID 1 on the leftmost corner, we can see that no matter how many layers you are using this quantum circuit, you are always not able to perform this entangling operation between the qubits, any of the two qubits, because there is no gates between any of the qubits here. And also we can see another one is the quantum circuit 9 on the rightmost of the axis. So here we can see that actually when we have a reasonable number of layers here, the entangling capacity of this kind of circuit is very large, because we actually have a lot of entangling gates between those qubit pairs, and then we can create an entangled states between all the qubits. All right. So besides this entangling capacity, so intuitively here, we actually want to have some quantum circuit that can have a large entangling power, because remember in the first lecture we introduced that we want to encode actually a large space of the data to the qubits. So only if we have a large entangling power between the qubits, we can leverage this large exponential Hilbert space. If we're not able to entangle them together, and then we cannot encode a large number of data to all of qubits altogether. So besides this expressivity and also the entangling capacity, we also have another measure, which is the hardware efficiency. So in the last lecture, we introduced that. Yeah, please, question.
So, if at layer 1, you're already maximally entangled, would you ever need multiple layers?
Yeah, that's a great question. So here we can see that one interesting observation that actually with a very small number of layers here, 1, 2, or 3, and then the entangling power here is already 1. So I think the value here is because of the randomness when we actually compute this MW measure. So the larger the number of copies of the layers, we have to sample more circuits to compute this measure. So if we are not able to sample enough, that's actually number is exponentially increasing. So, but the short answer is that for the entangling capacity, that is using 1 or 2 or 3 layers is not large enough. But for the expressivity, it's always better to have more parameters to learn. Yeah. Okay, great question. All right, so for the another aspect is the hardware efficiency. So basically, whether we want to implement those quantum circuit on the actual device. So we can see that, for example, if we have 5 qubits with this topology, and then we also need to consider what is the architecture of the quantum circuit, whether we can perform those operations natively on those quantum gates, quantum circuit or quantum device. So the first question is whether the PQC design consider the qubit connectivity. For example, in the previous one, we can see that there are connections between the neighboring qubits 0 to 1, 1 to 2, and 2 to 3. So in that case, we'd better to place those different qubits on the P0, P2, and P1. Right. So in that case, at least 2 of the gates can be directly computed. And also, we also need to consider whether the gates are native gates, right? So for example, here, the gates are the CZ gate. the controlled Z rotation case. So in that case, we also need to see what is the actually supported operation on the actual quantum device. If the operation is not directly supported, and then we have to perform a lot of transformation of the gates to decompose those quantum circuits to the native operations. And then the decomposition process will introduce also a lot of the overhead. So those are the several aspects we have to consider when we actually construct those quantum circuits. And for the encoding part, we also have multiple ways to encode the data to the quantum circuit. For example, consider a classical data X, which consisting of the M samples, and each of them has N features, right? So in that case, we need to encode each of the value or each of the vector to the quantum circuit to do the processing with the encoding module. So there are multiple ways of the encoding of encoding those different information to the qubits. So for example, we are going to introduce 4 different encoding methods. So the first one is called basis encoding. So that is very similar to the binary representation in the classical machines, right? So for example, if we have just one value, number 2, and then we have the binary representation of this value in the 1, 0, and then we can create a quantum state just representing this 1, 0 state. We have all the energy on the 1, 0 state. However, it is not very efficient because we can only encode one data. Say if the X here is 2, and then we have 1, 0, but if the value is 0 here, and then we just have all of the energy for this 0, 0 state. And if the value here is 3, we have to encode all the information or all the energy to the 1, 1 state. So this is not very efficient for only one data point. But if we have multiple data simultaneously, for example, we have the data set contains multiple values, for example, a vector of 2 with the value 0 and also value 3. And in that case, we actually can encode those data simultaneously because we are able to represent multiple values with a limited number of qubits. For example, here we can create an entangled state, the 0, 0 plus 1, 1, using the quantum circuit we introduced in the last lecture. Basically, we have the Hanrui gates and also a CNOT gate. And then we can create an entangled state between the 0, 0 state and also the 1, 1 state. And also, if we have multiple values further, we have 0, 1, and 3. We can also use a vector to have enough to have the same energy on basically all of the sectors here from the 0, 0 to 0, 1 to the 1, 1. So we also have other encoding, which is the amplitude encoding. So basically, using this amplitude encoding, it's very straightforward. So we just want to encode this input vector to the state vector of the qubits, right? So for example, if we have this input vector as 1, 0, 0, 0, so this is the input vector. And then we know that with 2 qubits, we can actually create a vector with the length of 4, right? So in that case, we can have just the first vector. All of the energy will be on the first qubits. In that case, we can create this 1, 0, 0 state. So if we have another vector, which is the 0.8, 0.2, 0.6, and 0.45 here, we can also allocate energy of the different states here to represent the ratio between different inputs. And then we can recover this input vector through the states of this quantum circuit. So in that case, for n features, you can imagine that we only need log 2 of n of the qubits, right? Because we are able to create a vector of 2 to the power of n with n qubits. So this is a very efficient encoding method. Yeah, question. That's that's a great question. So actually, we require the input the length should be 1. So the overall the length for example the norm 2 of each value squared and then something together we should have 1. In that case, typically what we did is to do a normalization first, and then we have a normalizing factor, and then we can encode the remaining information to the qubits. So in that case, we have to store the normalizing factor in a classical device. Okay. For another one is the amplitude encoding. Another example here. So basically, we have 2 values, and then similar to the previous one, we can concate them together, and then we can use this quantum circuit below to represent state. So the reason why I'm showing this quantum circuit is that although we are thinking that we have a large space to encode the data, actually the actual encoding process is not very trivial. So basically, we have to construct a very complicated quantum circuit to prepare the quantum state from the all zero state. Because initially all the qubits will be initialized to the all zero state, and then that means the vector will be 1, 0, 0, 0. And how can you prepare this arbitrary state from this 1, 0, 0 state? That is a large problem because we have to have a large number of gates in the middle to prepare the state that we want. For example, even if we want to just encode those 4 numbers, and then we have to use a large number of gates to represent the state. All right, so another one is called angle encoding. So basically, we can encode different data in the rotation angles of the qubit gates. So here is an example on the bottom right corner. So basically, if we have different values of the input data, and then we can encode those values to the rotation angle of the gates. For example, we have this RY gates on each of the qubits, and then if the input vector is this 0, pi over 2, and pi. In that case, we can just directly encode those values to the rotation angle of the qubit 0 and qubit 1 and qubit 2. So in that case, this way is very efficient because we don't have to perform any of the compilation process to construct those complicated circuits to do the state preparation. We can just directly input those values to the rotation angles of those quantum gates. And also, there are also several other ways to encode the data. So one way is called the arbitrary encoding. So basically, you can construct the combinations of those different previous encoding method. And then, for example, we can firstly have these 2 layers of the rotation gates, and then we can perform some entanglements between the qubits using those CNOT gates. And finally, we can use another layer of the several gates of the entangled gates to encode another remaining values in the classical vector, right? So in that case, we can see that for this vector with in total 12 values, we can use those rotation angles on the bottom to perform this encoding of those input data. So after we have those encoding process, we need to perform the training of the primary quantum circuit. So basically, the intuitive way to understand the previous encoding data is that, for example, you have this in the classical deep learning, we want to perform this image classification, right? And then the first step will be performing some of the, say, denoising or some of the downsampling of a very large input image. And right after that, you can apply those different layers of the trainable deep learning layers, like convolution or some other layers, to the input image. So just like here in a quantum device, the first step is to perform some pre-processing to encode the classical data to the qubits. And then after that, you can apply in different kinds of the parameterized quantum circuit to transform the input state to some of the target state to perform the classification or some other task. So typically, the parameterized quantum circuit training, they also use this data-driven method. So basically, we have a lot of parameters in the trainable layer, and then we want to do this iterative parameter updates according to the objective function, right? So basically, we have this iterative loop. So we have some parameters initially, and then we can firstly compute what is the objective function, what is the cost function. For example, for the classification task, we can still use the cross entropy loss. And then we can do the back propagation or some other optimizer to optimize those values to minimize this overall cost function. So one way to do that is to find a different differentiate method. So basically, we can just use this we can just have a small perturbation of the input data values, and then we can compute the local derivative of those of that point, and then we can use this gradient to update the parameters. So the accuracy actually really depends on what is how large is epsilon. Because if you have a very large epsilon here, and then the derivative you are computing is actually very different from the actual gradient. So for example, here, for the epsilon here, very large epsilon here, and then the actual gradient you are computing is very different from the gradient you are computing is actually very different from the true gradient. So in that case, the problem of the finite difference method is that you have to carefully select the epsilon value to compute the gradients. So in order to overcome this drawback, we also have another way to compute the analytical gradients for each of the quantum gates in the quantum circuit. So that is actually called the parameter shift rule. So in the parameter shift rule, here is actually the overall overview of the parameter shift. So basically, we have those different layers, different gates in the quantum circuit. The way to compute the partial the gradients of this the loss function to this rotation angle or to this value is that you can add pi over 2 to this value and then execute the quantum circuit again to compute the final loss function. And then you can distract this, you can subtract this pi over 2 value from the original theta, and then you compute the value again. So the final gradients will be the same as it will be the true gradients or the true analytical gradients. So here we are going to do that, explain that step by step. So basically, we want to compute the gradient of theta here with regard to the f theta, right? So the f theta here is actually the measurement outcome of this qubits, the first qubits. So we want to understand what is the gradients partial f theta here over partial theta. So in order to do that, we can shift the theta twice, right? So firstly, we can add pi over 2 to the theta, and then we can compute the function again, which is the f theta plus pi over 2. And then we can also shift the theta to another direction by pi over 2, which is theta minus pi over 2. And then the actual gradient of those partial f theta over partial theta can be directly computed as f theta plus pi over 2 subtract f theta minus pi over 2 over 2. So why is that the case? So that seems to be not very intuitive, right? So actually, I'm listing the actual the proof of this process here in the slides, but I'm not going to show all the details of those process. So one very intuitive way to understand that is that, for example, if we want to compute what is the gradient of the cosine function, right? So we know that if we compute the derivative of cosine, and then the function will be a sine function, right? So that would be cosine theta plus over pi over 2, right? So actually, when you shift the cosine function, this periodic function by pi over 2, that is actually aligned with the derivative function of this original function. So that's the intuitive understanding of how we can just shift the original value by pi over 2 to compute the gradients for this angle. Because as long as we are using those rotation angles, because of the mathematical representation of those values, those cosine, for example, if we are doing this rotation x, and then we can always do the decomposition for convert to the exponential representation, and then we can know that the basic element of them is actually the cosine and sine functions. So that's why we can directly use those parameter shift rules to compute the analytical gradients instead of the estimated gradients. Okay, so basically, another way to do the gradient computation is of course the backpropagation, which we are very familiar with in the classical deep learning. So we can compute using the chain rule. We can compute the gradients for each parameter on the whole computing path. So here actually we are doing some experiment to show that actually using the backpropagation, we are of course getting the analytical gradients of those values, and then we can also verify whether our parameter shift rule computed gradients align with the backpropagation. So here, basically, we can see there are two plots here, and on the top one here is actually showing two different gradients here. So one is in the blue, which is the gradients computed by the backpropagation, and also for another one is using the parameter shift rule. So we can basically see that all of them are aligned to each other. So that means using the parameter shift can always give us the same result with the backpropagation, and which are the analytical gradients of the value. So however, the backpropagation, as you know, we have to understand what is the we have to have the whole computing graph. So we can do that on the classical device, right? So we can compute the first layer, and we know all the intermediate results, and then we can do the backpropagation. However, if we're computing that on the actual quantum device, we cannot obtain the intermediate results, right? So that's why actually the backpropagation can only be done on the classical simulator, because in that case, we have the whole computing graph. However, on the actual quantum device, we're not able to obtain all the intermediate results. So that's why we cannot perform the actual backpropagation on the real device. So on the real device, on the other hand, we can perform this parameter shift rule, because on the real device, for the parameter shift rule here, we actually don't require any of the intermediate results. We only require the final output from the device. So that's the reason why we can always rely on this parameter shift rule to compute the gradients. But for the backpropagation, it's only suitable for the classical simulators. So here we can see, as we said, it is doable to perform the parameter shift rule on the actual device. So how exactly can we do that, right? So for example, here we have the rotation x theta gate. So we want to understand what is the partial f over this partial theta value, right? So in marked by the yellow block here. And then on the actual quantum device, so we can firstly perform this quantum circuit without the shift to obtain the f function values, which is the original value. And then we can compute this classical part of the forward loop, because we can, for example, we want to perform this classification task, and then from those F1, F2, all the way to F4, and then we want to perform, say, the softmax function, and then we can compute the cross entropy loss according to the classification result. And then after that, we can perform this backpropagation on the classical side, because on the classical side, we can always record the intermediate result, right? So in that case, we are able to obtain this partial loss over the partial f, where f is actually the measurement outcome from the qubits. And then on the actual device, we can perform this shift rule, right? So because we want to compute what is the partial f over the partial theta. So overall goal is to compute the partial loss over the partial theta. So we can use the chain rule to separate that to firstly partial loss over partial f, and then partial f over partial theta. So for this partial f over partial theta here, we can use the parameter shift rule we just introduced, right? So in that case, we can sum over those four passes because of the summation principle, and then we can use the chain rule to compute the value for the overall partial loss over the partial theta, which is the on the bottom right corner, which is actually using we can obtain this partial f over partial theta using the parameter shift rule on quantum device, and then on the classical device we have this partial loss over partial f, and then we can do the overall computation of partial loss over partial theta using this chain rule. So after this computation, we can understand, or we can obtain that what is the derivative of this theta value, what is the impact of the theta value to the final loss, and then we can update the theta according to our goal, either that's a classification task or some other generation tasks. Yeah, question.
Like twice for every parameter or every update. That seems like it might not scale well if you have like parameters. So then any ways to do these shifts in parallel?
Yeah, so that's a really great point. So you actually capture one of the fundamental challenge of the parameter shift rule, which is the for each of the parameter, analytically, we have to just shift that only value with all the others remain the same, right? So in that case, the number of actual circuit run scale linearly to the number of parameters. So that's actually not very scalable. So that's the reason why there are actually many research. For example, we can do the simultaneous perturbation, SPSA, so which we'll introduce later. So we have some ways to approximate this process. We don't have to rigorously keep the other values the same, but we can perturb a subset of all the parameters altogether. So in that case, we can reduce the coefficient. But in general, the reason that's the case. We have paid the linear cost to the number of parameters. But that's also the case for the classical deep learning. You also have the linear scaling training costs if you have a really large number of parameters in the classical neural nets. But we have some way or some ongoing research trying to reduce the coefficient, reduce the scaling factor. Yeah. Okay. Cool. All right. So here comes we're going to introduce some of the training technique, including the SPSA. We will also introduce in the actually just next slide. So the vanilla gradients descent is that we for many different iterations. So this is just a very intuitive or very conceptual plot. So we want to make sure we reduce the loss function, right? For example, we want to do the quantum classification. We want to train those parameters until we converge to some of the target with a satisfactory accuracy. And so just as we discussed, if we just do the circuit execution for each of the parameter, and then the number of circuit run will be 2 times n, where n is the number of parameters, right? So in that case, it's a very costly process to train all the parameters. So in that case, there are actually the algorithm called SPSA, which is simultaneous perturbation stochastic approximation. So the basic idea is that we can actually we don't have to just keep one value changed. We can actually change all the values altogether, right? So for example, we can perturb all of the parameters in the quantum circuit altogether, and then we can obtain this value, obtain this vector, which is the f theta plus epsilon minus f theta minus epsilon. So in that case, we can actually, our assumption is that when we actually perturb all the parameters together, the value will be not very far away from the previous perturbation of only a small number of value or even only one value, right? So the hope is that when you actually do this process, the new value on the top here is very close to only perturb one value. So in that case, because we are changing a very small epsilon to each of the parameters, so in that case we can consider those two very close to each other, and then we can use this. And then, however, after we compute this gradients, we will have gradients for each of the parameter here using the SPSA, because we will have the vector. Some of the perturbation will be +1, some of others will be -1, right? So in that case, we can compute one single value gradients for each of the parameter, and the magnitude of that value will be always the same, but direction for that value of each parameter will be different. Some of them is on the positive direction, some others on the negative direction. So that's how we can perform this simultaneous perturbation to compute all the gradients of all the parameters in just one round of this forward process. So here we can see what is the performance of this SPSA compared to the vanilla gradient descent. So basically, we have multiple like curve here. So the first one in the blue is the vanilla gradient descent, right? So just using the back propagation or using this just using the this natural this finite difference, and then that will be the blue curve. But using the SPSA, we can see that it's very close to the vanilla gradient descent. And then we also have this quantum natural gradient. So that is in that case, the performance of that one is the best, but the cost of that one is much larger than the vanilla gradient descent or the SPSA. Okay, so there is another issue that I want to also introduce or mention a little bit, which is the baryon plateau issue. So in a classical deep learning, we know that after we stacking many layers of the neural nets, so there will be a gradient vanishing problem, because when we're actually doing too many layers of the back propagation, and then the gradients of the first layer will be too small to update. It will be too small to update meaningfully change the parameter values. So that's also the similar case in the quantum circuit. So basically, if we have a very large number of qubits, and then we have many different layers, a large number of layers, and then the gradients of the first several layers will be also very small. So here we can see that intuitive plots here. So the x-axis is the number of qubits, and the y-axis is the variance of the gradients. So we can see that when we have a larger and larger number of qubits, the variance of the gradients will be reducing exponentially. So that's actually one of the bottleneck, or one of the ongoing challenging point of the quantum machine models, which means we cannot stack too many layers in a quantum circuit because of this vanishing gradient problem. Okay, so and then here, yeah, question. Yeah, that's a great question. So in the classical side, classical deep learning, we have this residual connections at the bypass, right? So we can directly have those different layers of the back propagation of the gradients all the way to the first layer. So actually, there are some similar process in the quantum to adding this bypass layer to the quantum circuit, but there are in general they are not working greatly. So the reason for that is actually on a quantum device we cannot copy the state of an intermediate state to the later layers, because we cannot directly, there is a non-cloning theorem I actually read here. So we cannot directly clone the state of all the qubits to a new set of qubits. So it's not like in a classical device. It is very easy for you to clone one value or all the values of a layer and then bypass that to the final layer. But on a quantum device, you are not able to do the cloning of the qubits. So that's why we cannot create two copies of the state and then merge them all together in the later layers. So right. So in that case, the using the residual connection is not a solution, or it's not a complete solution for the quantum learning right now. Yeah. Great question. Okay. So now we can have a recap of the quantum classifier we just introduced in the previous lecture. So basically, we have this encoder. We can encode those pixels as the angles with this rotation angle encoding. And then we have those trainable layers, those unitary U3 layers. U3 is basically you can arbitrarily changing the states. And then also we have the controlled U3 gates, so we can train those parameters using the SPSA method or using the finite difference method. And then after that, we can do the measurement of the qubits and then do some of the post-processing to obtain this classification results. So here we can see basically this training process is also similar to the training process of this classical neural net. So if we have here on the left-hand side is visualization of this optimization process. We want to make sure we are going to the minimum places to converge to that point to have a good prediction result. So besides this classifier, actually, there are also other tasks that we can use the parameterized quantum circuit. So one task we can do is actually the variational quantum eigensolver. So the basic task for this variational quantum eigensolver is to find what is the smallest eigenvalue given a matrix, right? So that is, for example, we can decompose that matrix to multiple Pauli matrices, and then we can measure that for multiple times. And then the variational quantum eigensolver is actually trying to prepare a state, which is the eigenstate corresponding to the smallest eigenvalue. So you can imagine that we can prepare this state and then evaluate what is the value, what is eigenvalue for that state. And then we can always tuning the parameters in the quantum circuit to approach the final eigenstate, which has the smallest eigenvalue. So finding the smallest eigenvalue have a lot of applications. For example, we can use that to find the ground state energy of some molecule. We can represent the molecule Hamiltonian state. We can represent the molecule feature with the Hamiltonian matrix. And then if we find the smallest eigenvalue of the Hamiltonian matrix, that will be the smallest ground state energy. So that is that means that for the stable process, for example, if we want to understand what is the stable length of the bond between some of the atom inside the molecule, and then we can simulate or compute the energy for different distance, right? So in that case, because the chemistry reactions will always go to the state which has the smallest energy, right? So in that case, we can understand after this chemistry process, what would be the length of the bond between all of the atoms. So this is one of the application of the parameterized quantum circuit. So another one is the QAOA or the quantum approximate optimization algorithm. So using the QAOA, we actually can find solve the combinatorial optimization tasks. So in short, those are some of the some of the PQC tasks, the classifier for the machine learning task, the BQE for quantum chemistry, or some of the QAOA algorithm for the combinatorial optimization tasks. Okay, so let's continue to the section 4, which is the noise-aware on-chip training. So we have introduced that how to construct a quantum circuit. So actually, on the real device, there is a large impact of the noise when we're actually doing this noise gradients computation. So actually, the noise can reduce this reliability of the on-chip computing gradients significantly, right? So here we can see that there is a noise-induced gap between those two curves. One curve in the blue is actually the classical training, which means we just simulate all of the process on a classical device, and then the red one here is actually showing the actual parameter shift rule on the real device, on the IBM quantum device. So we can see the accuracy of this evaluation process can be significantly reduced by this noise on the actual device. So how can we deal with that, right? So here we have a very interesting observation is that when the gradient's magnitude is very small, and then the relative error of that will be very large. So it's also very intuitive. So imagine that if we have a very large gradient value, and then the noise on that noise is more unlikely to change the direction of those gradient. But if the gradient is very, very small, you can imagine only a small noise, a small perturbation on a real device will change the direction of the gradient. So in that case, the overall idea is that we can find those very small value of the gradients, and then we can prune those unreliable gradients during the training. We only use those reliable gradients to perform this parameter updates, right? So in that case, here we propose a method called this probabilistic gradient pruning. So the basic idea is that before this pruning, we actually, in each of the training step, we can always performing the updates of all the parameters, right? So, and however, using this gradient pruning, we only perform those update of those those parameters with very reliable gradients. So how can we know whether the gradient is reliable enough? So actually, we just see what is how large is the gradients that we computed from the this process, right? So specifically, before this pruning process, we are updating all of the parameters on the left-hand side. And using this gradient pruning, we are only updating a subset of the parameters with the reliable gradients. So in order to determine which subset of the gradients is reliable enough, we actually have this iterative process, the window-based method. So we can firstly have an accumulation window to accumulate the gradients of multiple steps, to accumulate the absolute value of those gradients. And then, for example, we can accumulate for 3 steps to see how large are the gradients for each parameters. And then we can do a summation of all of the absolute value of the gradients for each parameter, and then we can do a sorting. We only use those values with a very large, only use those gradients with a large value to perform those pruning process. And for those gradients, very small gradients, we will not use them to update the parameters of the quantum circuit. So let's make sure that we are only using the reliable information to update the parameters. Okay, so we are actually comparing this QC train using this probabilistic gradient pruning compared to the other ones. So basically, we are able to improve around like 5% to 10% of the accuracy on this 4 classification tasks using this probabilistic gradient pruning method. And also, we can see that for this accuracy on this fashion 2 on the San Diego machine on the IBM device, we can achieve around 2x of the training time reduction, because for those unreliable gradients, we not only don't use them, and also we actually don't have to compute them for the from the first perspective. So we actually don't have to doing the computation for those unreliable gradients. We only compute those reliable ones. So here we can see that the gradient pruning for different times of the inferences. So the axis here is the number of inference we are doing on the real device to compute the parameter shift rule gradients. And then the y-axis is the test loss. So the loss is the lower the better. So we can see on the classical device, there's no error at all. So we can see the loss is always the lowest. And then the blue curve here is the QC training, which means we are using the real device to perform the parameter shift rule. And then because of the noise, there will be a gap between the ideal case to the blue curve. And for this quantum on-chip training, we are able to close this gap to further push this curve to the ideal case, to the gray curve. And also, the on-chip training here is actually also very scalable, because we are not using any of the classical process during the whole training pipeline. We are computing those gradients on the real device, and then real quantum device, and then update the parameters. So imagine that if we're using the classical simulator, and then the cost, for example, the runtime cost or the memory cost will be exponentially large when we have a large number of qubits, because the size of the state vector will increase exponentially to the number of qubits. But using the quantum device to train the model, we don't have to pay the exponential increasing cost in terms of the runtime and also the memory. So here we can see the probabilistic pruning. We also compare to the deterministic pruning. So basically, in the probabilistic pruning, we are using the magnitude of those values to determine which parameter has a larger probability to be pruned. But this process is not deterministic. So that means we are not always or removing the parameter, the gradients forever. We are using the sampling method to sample those different values to prune. So that is also give us some advantage compared to the deterministic pruning method, around like 1% to 9% of the increase of the accuracy over the several different tasks. All right, so we also actually developing a library which is called the TorchQuantum Library, which we are actually implementing all of the classical process using this PyTorch framework. Because all of us are very familiar with the machine learning process, and we are using this PyTorch framework or TensorFlow, if Google prefer the Google frameworks. And then actually Google have their own quantum framework, which is called TensorFlow Quantum. But for the PyTorch, we are actually developing the TQ framework, the TorchQuantum framework. So we want to make sure the developing of these quantum machine models has a very good infrastructure to start with, right? So we want to make sure the developing of those models have a fast speed and also very convenient to use, and very easy portability between different frameworks among those common quantum IRs, and also scalable computation. So, and also we want to have those GPU acceleration process, and also those density matrices support, and also different converters to other frameworks. And also in the PyTorch, we know one of the advantage is the dynamic computation graph, that we can have intermediate results very easily, and that can facilitate our debugging process. So basically, here I'm just going to show a very simple example using the TQ framework to construct a quantum machine learning model. So basically, this is very similar to constructing the classical neural networks. So we have this model which is a child class of the n-dot module, and then we can firstly instantiate a quantum device using the TQ.quantum device, and we can specify how many qubits with the number of wires. And after that, we can also specify the encoder gates. So remember previously we introduced this rotation angle encoding. So we can have those rotation X, rotation Y, and also all the other 4 layers, the Rx, Ry, Rz, and Rx. And then we can also specify some of the trainable gates. For example, we have those rotation X gates to train, right? And also whether those have parameters or not, we can specify them in the init function. And also we have that is basically the construction of the model. And how can we use that, right? So we also have this forward function, the same as the other classical PyTorch models. So basically, we have this, we want to firstly reset the quantum device vector, reset the state vector. And then we can encode those classical pixels using those encoder layers, right? So just like the diagram we are showing, we have those different layers to encode the classical images. And then we can apply those trainable gates to different qubits. And then we can apply those non-trainable gates. For example, some of the Hanrui gates or the SX or the arbitrary unitary, we can apply some unitary gates, arbitrary ones, to the qubits. And then finally, we can measure this, we can have this measure process, the measurement function to measure the qubits device back to the classical values, right? And then after that, the X here will be purely classical value. And then you can apply any of the your favorite classical layers, either it's a MLP layer or some attention layer or any other ones. After we obtain these values from the quantum device on the classification side. And then finally, we can do this, we can perform the softmax to obtain this final classification task, or either you can also perform some generation task using this framework. So basically, as we introduced, we have this quantum device supported as the TQ.quantum device, and also we can perform different ways. So just like in the PyTorch, we have this PyTorch.torch.n.functional. We also have the TorchQuantum.functional, similar to the quantum PyTorch syntax. And also we have another supported gates, supported way to perform the gates. We can instantiate the gates first, and then we can use that gate to process the value, the quantum device. And also we have we can perform this. The third way of performing those gates is that you can directly initialize this quantum state, and then you can use the quantum state.h to perform the gate. So the underlying implementation of the TQ is actually using all of the data structure in the PyTorch, right? So for example, we are using the state, we're using the torch native operation, the torch zeros to initialize. And also all of the operations, all of the unitary gates, we're also using the PyTorch tensor. So in that case, you can imagine the classical simulation process or any of the quantum machine learning forward process will be fully differentiable. So we can very simply use all of the off-the-shelf optimizers provided by PyTorch to optimize our quantum machine learning model parameters. All right, so we also provide some of the macros basically some of the macros in the framework. So we have this amplitude encoder. You can directly use the TQ.amplitude encoding to call that, and also TQ.phase encoder to call this angle encoding using those rotation values. And also, of course, we have this supported way to convert those TQ models to other frameworks like the Qiskit. So if we want to run those quantum circuit on the real quantum device provided by the IBM quantum platform, we can also use some of the functions that we already baked in the TQ framework to directly write those converters. And then we also provide some of other functions to draw the circuit or constructing some of the predefined layers, and also some different kinds of quantum machine learning models that are read in the library that we can directly use. Welcome to check it out. So I will not introduce all the details of the model. So you can just go to torchquantum.org or search TorchQuantum on the GitHub to play with the library. All right, so in the final section, we'll introduce one example that we can use the TQ to perform some of the robust quantum circuit architecture search. So actually, the quantum circuit architecture search is one of the fundamental challenge in the quantum deep learning. So that's actually also the challenge in the classical deep learning. So I believe that in the previous lectures we have learned some of the neural architecture search of the models, right? So you don't know how to construct a model which is that is the best suitable for the target task. So you can do some of the NAS method, the neural architecture search to find the best model. So that's also the case. That's also the challenge for the quantum machine learning. So basically, you have a large design space. You can perform many different kinds of the gates. For example, we have many different types of the gates, either the U3 gates or the NOT gate or C0, or you can have different numbers of gates, right? So you can just put one layer, or you can stack as many layers as you want. And also the positions of the gate is also very different. So if you're directly applying this U3 gates in the first layer, or you can do some perturbation of the gates. So there's essentially a very large design space for us to explore. So how can we find the best quantum circuit to perform the target task, right? So for example, if we want to perform those this kind of classification task, what would be the best quantum circuit structure to start with, and also what are the structure for some quantum generation tasks, right? So here we're going to introduce this framework called quantum NAS, the quantum noise aware search, to perform those search process. So of course you can use any of the naive search method that is already available or already widely used in the classical deep learning. For example, you can just have a random search, right? So you can have many of the different structures, and then you can train each of them according to our previous process, and then you can evaluate the performance of each of the quantum circuit on the real device to see which one is the best. However, if you are doing this search process, for example, you can have many different. For example, you can have many different layers of the quantum circuit. Then you have many gates for each of them, right? So, so in that case, you actually have many different combinations. You can just use one gate in the first layer and two gates in the second one, or all the gates in the third. So there is actually a very large design space, right? So one way you can do the search is to just train many different circuits. You can train one here, right? And then obtain the performance, 90% of this, or you can train another one here. Maybe this one was 80% of accuracy. However, that way is not very efficient, because you can imagine you have to train each of them to obtain the accuracy and then find the best one. So the goal of the quantum NAS framework is actually whether we can just train once, right? Whether we can train a superset of all of the possible circuit, a superset of that here, and just train once, and then we can sample the parameters from that super circuit and then directly evaluate on the real device to obtain the performance. So that's the basic idea behind this quantum NAS framework. So you can train once, but use many. So it's similar to the classical like one single pass, one shot of the NAS method. So there are actually 4 steps in the framework. So the first one is that we can construct a super circuit, right? So we want to make sure the super circuit has a large enough representing power. So we can construct, say, we have 3 layers here, and then each layer has, say, 4 gates or 9 gates. And then we have at maximum, we have 9 layers. And then we can, after that, we want to train this super circuit. And then after training, we can do some noise aware, this evolutionary search of this sub-circuit and also the qubit mapping. And then after we find this reliable circuit, and then we can train this from scratch. And finally, we can also perform this pruning method of those values. So let's go through them one by one. So the first one is the quantum super circuit and sub-circuit. So as we just introduced, we want to construct, we want to cover a large enough design space, right? So for example, the super circuit with this U3 and CU3 gates. So we have many different candidates in the design space. Those are called a sub-circuit, right? So during the training process, the reason why we're using a super circuit is that we can just do the training for this super circuit for once. The question.
So in this sense, this example is verified. We still something about the same.
Yeah, so the issue for the barren plateau is actually still there, but there are some of the actually this method is orthogonal to the quantum circuit structure that is can kind of solve the barren plateau issue. So we are proposing that inside this design space, how can you find the most reliable circuit, right? But you can start with a design space that have a better immunity to the barren plateau issue, right? So, or the short answer is that this method cannot directly solve the barren plateau, but we can firstly start with a design space that has a good property, or we can, during the search, we can evaluate the gradients to find those ones without the barren plateau issue. So that can always be done during the search process, right? So either you want to search a very reliable one, or you want to search one without the barren plateau issue. Yeah. Okay, so let's continue. So basically, those when we're actually using the super circuit method, we want to make sure those sub-circuit can inherit the values directly from this super circuit. So we don't have to train those values again. So we just train the super circuit once, and then we can use that for the evaluation of all of the sub-circuit in the design space. So in order to achieve that, so you may be wondering how can we do that? Because those values typically cannot be inherited by all of the sub-circuit, right? Because if we are training those individually, and then the final value, for example, if we train this sample circuit individually, right? Even they have the same location of the gates, they may have different values. Why we can directly inherit that one to all of the sub-circuit, right? So that is seems to be impossible. So here actually we are introducing one heuristic to train this super circuit, right? So that is this sample and training process, right? So for each of the step, we actually can sample a sub-circuit from this super circuit. We just sample a subset during this training step. And then we only do one time of the parameter updating. For example, in the first training step, we can sample this structure and then update the parameters inside this structure. And for the second step, we sample this structure and then we continue to update values, right? So in that case, after enough number of training steps, we can imagine that all of the sub-circuit in the super circuit are already undergoing the same number of training steps, right? So even though they are not the same level of accuracy compared to the train from scratch sub-circuit, they can still indicate what is the performance or the relative performance order between all of the sub-circuit. So here we can see a quantitative result for that. So basically, here on the x-axis is the loss function for those sub-circuit using those inherit parameters, and the y-axis is the values that is the ground truth, basically the loss that we train from scratch. So we can see a pretty good positive correlation between those two. So that means because we are just want to find the one with the best performance, so we are only caring about the order preserving property between the sub-circuit with the inherent parameters compared to the all of the sub-circuit trained from scratch. So in that case, we only need to make sure this correlation between those two are very, very large. So in that case, we can use this super circuit to facilitate the later search process. So we can do the evolutionary search inside this sub-circuit. Basically, we can search for we can use a reinforced learning or any of the search engine, your favorite search engine, and then we can sample the sub-circuit from this super circuit, and then we can evaluate the performance on the real device, and then do this iteratively until we find the best sub-circuit. So we are also as we learn in the first several lectures, we also have the pruning technique that is also applicable to the quantum machine learning domain. So basically, some of the gates after we train those sub-circuit can be very close to zero, right? So as we introduced in the previous last lecture, so if we have a value very close to zero, and then the actual unitary matrix is actually a identity mapping between the input and output. So in that case, we actually don't have to perform the actual implementation of this gate. So if the value, for example, rotation of the 0 degree, and then the actual result will be same as the input, right? So in that case, we can also perform those iterative pruning of those values very close to zero. So basically, we can find we can do a search of those values or those gates close to zero. Yeah, question.
Actually, I'm wondering whether it is scalable, especially during the large number of videos.
Yeah, that's a great question. So basically, we can do remember that we introduced the parameter shift rule in the last section, right? So the super circuit training process can also be done on the real device, right? So we can use the parameter shift to train the super circuit. So all of the process, the super circuit training, the sub-circuit training, and also the search can be done on the quantum device. So that's actually scale with the number of qubits. Right. Great question. Okay, so after that, we can do this pruning process to remove those small value gates to make sure our the final resulting circuit is most efficient, containing the most essential message. All right, so there are also some other search frameworks, for example, the one that using the machine learning based predictor. So basically, you can train a model to predict which subcircuit has the best performance, right? So we can use some graph neural networks to approximate the structure of the quantum circuit and then train a predictor on a real device. And then there are also some other framework that directly encode the structure of the quantum circuit using a graph. Right, so for example, if there are 3 different qubits, we can use 3 row of the pixels to encode the data. And also some other framework using the reinforcement learning for the architecture search. And then here we have this quantum computer on the top. And then the action will be generate whether we want to add one more layer, right? So we can do that using a bottom-up approach. So whether you want to adding one more layer or reducing one more layer, right? So there are action space, and then you can evaluate the performance on the real device to generate the reward and also the observations, and then you can feedback to the RL agent to decide the next action. And also there are some other work using the differentiable search and also some proxy-based search, which I'm not going to all the details, but welcome to check out those papers. So finally, a summary of today's lecture, we introduced the parameterized quantum circuit, the training process, how to do the classification using the simple classifiers, and also how to improve the reliability using those noise-aware parameter search, the TQ library, and also how to find the most robust quantum architectures using this quantum NAS framework. All right, so with that, thank you very much for your attention. Happy to take any questions. Thank you. And also have a nice Thanksgiving.